Okay, let's unpack this. We spend a lot of time on this show talking about the what-ifs.
Yeah.
You know, the white papers, the theoretical
All
models.
those glossy renderings of cities that don't exist yet.
Exactly. Usually a lot of targets for 2050 or something. But today is a bit different. It's January 27th, 2026.
Right.
And the stack of sources we're looking at, it doesn't feel like a proposal. It feels more like a receipt.
It really does. It's one of those moments where the future just stops being a concept and becomes steel and concrete.
We are looking at the NEOM Green Hydrogen Project, and I want to set the scene immediately because the sheer scale here is actually hard to wrap your head around.
It is.
We aren't talking about some pilot plant in a university lab, where they run a couple of buses for a photo op. We are talking about the single largest commercial-scale green hydrogen facility in the world.
And it's situated in the Oxagon Industrial Zone of NEOM, so northwestern Saudi Arabia.
Right. And the mission here, if we boil all these technical specs and financial reports down, is to basically prove you can do the impossible.
They are trying to produce renewable hydrogen on a massive, massive industrial scale in the middle of a desert without a single ounce of carbon emissions.
And that's the key distinction, isn't it? We aren't talking blue hydrogen, which, is made from natural gas with carbon capture.
Right.
We aren't talking gray hydrogen. This is the real deal. Green hydrogen.
Which honestly feels like something out of a sci-fi novel from 10 years ago.
Yeah.
But here we are, 2026, and the construction updates say this thing is nearly done.
It really is a pivotal moment for the global energy economy. I don't say that lightly. We are witnessing the shift from a hydrocarbon economy to a green molecule economy.
A green molecule economy. Okay, I want to put a pin in that phrase because we were definitely coming back to it. But first, let's look at the players.
Yeah.
Because you don't just wake up one morning and decide to build an $8.4 billion facility in the sand.
No, you certainly don't. This is a massive joint venture. You have 3 players, all holding equal stakes. First, you have NEOM itself.
The landlord and the visionary. Essentially, yeah. They provide the location and the strategic mandate under this whole Vision 2030 plan. Yeah. Then you have ACWA Power.
Okay, they're the local heavyweight champions, right? For renewable power, water desalination.
Exactly. They know how to build this kind of infrastructure in this specific terrain.
And the third leg of the stool.
Air Products. And in many ways, they're the linchpin here. They are a global leader in industrial gases. They bring the technology, the know-how for managing hydrogen, but maybe more importantly, they are the exclusive off-taker.
Okay, pause there. Off-taker. That sounds like a bit of corporate jargon. Why does that matter so much to someone listening right now?
It matters because it's pretty much the only reason this project exists. An off-taker is a guaranteed buyer. Air Products has legally agreed to buy 100% of the green ammonia produced by this facility for the next 30 years.
30 years. So before they even tightened the first bolt, they knew they had a customer until the mid-2050s.
Exactly that. It just removes all the market risk. It convinces the banks to lend the billions of dollars needed to build it. Without that signature, this is just a very nice drawing in the sand.
Okay, so let's get into the beast itself, the scale. I was reading through the energy input requirements, and I really did have to double-check the zeros. To make this work, they need a staggering amount of juice.
The energy demand is just immense. I mean, because electrolysis, splitting water is incredibly energy intensive. So you need a dedicated renewable power supply that's completely sort of off the grid to ensure it's truly green.
So what are we looking at? What's the number?
Total capacity is approximately 4 gigawatts of dedicated renewable energy.
4 gigawatts. For context, a typical nuclear reactor is maybe 1 gigawatt. So this is like 4 nuclear reactors worth of power.
But all of it coming from the sun and the wind.
Wow.
Precisely. And it's a hybrid system, which is the really clever part.
Yeah.
You have over 2.2 gigawatts of solar photovoltaics.
Just an ocean of glass.
And then you have over 250 wind turbines, contributing about 1.6 gigawatts.
Can you just visualize that? You're standing out there in the Oxagon region. It's hot, it's dusty. In one direction, solar panels stretching to the horizon. In the other, 250 massive turbines spinning in the wind.
It's a striking visual, but it's also an engineering necessity. The biggest criticism of renewables has always been intermittency.
The sun sets, the wind dies down.
And industrial plants hate that.
Oh.
They need a flat, steady line of power. You can't just turn the hydrogen factory off because it gets cloudy.
No, you'd ruin the equipment.
And destroy the efficiency. So they use the solar for the daytime peak. But in that specific region of Saudi Arabia, The wind profile is actually quite strong in the evenings and at night.
Oh, that's smart. They complement each other.
They hand off the baton, and for the little gaps between that handoff, they have a massive battery energy storage system.
Shock absorber.
That's it. It just smooths out the jagged edges of the power supply so the plant sees a nice steady flow of electricity.
Okay, so we've harvested this infinite flow of energy from the sky. Now we get to the alchemy. Turning electricity into fuel. This is the part that always feels a bit like magic to me.
It's the heart of the operation. Electrolysis.
Which, if you remember high school chemistry, is just sticking 2 wires in a beaker of water and watching bubbles form.
That's the principle. But, scale that up to 2.2 gigawatts of capacity. We are talking about hundreds of standardized electrolysis modules. The electricity just rips the water molecules apart. Oxygen goes one way, hydrogen goes the other.
And the output from that?
Roughly 600 tons of hydrogen per day.
600 tons. That is a lot of gas. And this is where I usually get stuck on these projects. I mean, hydrogen is a nightmare to deal with, isn't it?
It is.
It's the lightest element in the universe. It wants to escape everything. It makes steel brittle. If you try to ship 600 tons of hydrogen gas across the ocean, you'd need a fleet of ships the size of cities kept at near absolute zero. It's just a logistical headache.
And you've hit on the exact bottleneck that stalled the whole hydrogen economy for decades. Shipping pure hydrogen is technically possible, but, well, it's economically ruinous.
So NEO isn't shipping hydrogen?
No. They're adding a crucial second step to the factory line. They're taking that green hydrogen and running it through a synthesis loop to combine it with nitrogen.
And nitrogen is just from the air, right?
Yep. They have air separation units, giant vacuums, essentially, that pull nitrogen right out of the atmosphere. You mix the nitrogen with the hydrogen, and you get NH3.
Ammonia.
Green ammonia.
No, when I think of ammonia, I think of window cleaner. Or fertilizer. It smells terrible. Why on earth is this the solution to the world's energy problem?
It's all about the physics. Ammonia is a liquid at very mild pressures and temperatures compared to hydrogen. It's much, much denser. And crucially, we have been shipping ammonia around the world for 100 years to make fertilizer.
So all the infrastructure, it already exists.
The ships exist, the ports exist, the safety protocols are already written. It's a solved problem.
So the ammonia is basically a suitcase.
That is the perfect analogy. Ammonia is the suitcase for the hydrogen. You pack the hydrogen molecules inside this nitrogen suitcase. You put the suitcase on a ship.
And send it off.
You send it to a power plant in Hamburg or Tokyo. And when it gets there, you can either burn the ammonia directly, or you can unpack the suitcase, crack it back open, and take out the pure hydrogen.
That is incredibly smart. It bypasses the need to invent a whole new global shipping system.
It creates a bridge to the future using the infrastructure of the past.
And what's the volume here? How many suitcases are we talking about?
The facility is targeting 1.2 million tons of green ammonia per year.
1.2 million tons. That is not a science experiment. That is a commodity stream.
It's enough to make a measurable dent in the carbon footprint of global heavy industry.
So we've got the tech stack, solar and wind to electrolysers to ammonia synthesis to ships. Let's go back to the money again. You said $8.4 billion.
Yes.
That is a serious, serious bet.
It's a massive capital deployment, but it's also a strategic one. If we connect this to the bigger picture, this is really the crown jewel of Saudi Arabia's Vision 2030.
The big diversification plan.
Right. For 80 years, Saudi Arabia's wealth has come from geology, from what was trapped under the sand. But they've realized the world is changing. And they have 2 other resources that are just as abundant as oil.
And sunlight and wind.
Sunlight and wind.
Yeah.
And vast amounts of empty land near shipping lanes. So Vision 2030 is about pivoting from being an energy extraction economy to an energy production economy.
It's a hedge, isn't it? If the world stops buying oil, they'll be selling the green alternative.
And they'll be selling it to the same customers. This isn't for local use. This green ammonia is destined for global export. I mean, think about Japan or South Korea.
Right.
They're industrial giants, but they don't have the land or the sunshine to produce green hydrogen at this scale.
Right.
They are energy hungry, but resource poor.
So Saudi Arabia is effectively bottling their sunshine and shipping it to Asia and Europe.
That's exactly it. Exporting the weather.
Exporting the weather? I love that concept. It shifts the whole idea of what a natural resource even is.
Well, it democratizes energy in a way, but it also creates new power players.
Okay, let's ground this back in the reality of today. January 27, 2026. I feel like for years, every time we talked about NEOM, it was all rendered images and press releases. Where are we in the physical world?
We are. We are pretty much at the finish line. According to the construction updates in our source stack, the project is approximately 80 to 90% complete across the major segments.
90%. So the steel is in the ground.
Oh, it's physically there.
Yeah.
The solar farms are installed, the wind turbines are up, the grid transmission lines connecting it all are strung. Right now, they are deep in the installation phase for the really complex chemical equipment, the storage vessels, the cold boxes for the air separation.
They're wiring up the nervous system.
Exactly. And the timeline is very tight. The renewables, that 4 gigawatts of power, they're expected to be fully commissioned by mid-2026. So just a few months away. Then the electrolysers, the real core technology, will be commissioned in late 2026. That's the big test. Turning them on and ramping up the current.
And then?
First, full production and export is expected in 2027.
So literally next year. Ships will be leaving the port at Oxagon filled with green ammonia produced by the sun.
That is the plan. And given the financial pressure of an $8.4 billion investment, you can bet they are pushing hard to hit that date.
It's fascinating because it feels like we just skipped the pilot phase entirely and went straight to industrial revolution.
Well, that brings us to the why it matters part, doesn't it?
Yep.
Why should you care about a plant in the desert?
Besides the sheer cool factor.
Besides the cool factor, yeah. The headline statistic is the environmental one. This single plant is expected to save about 5 million tons of CO2 per year compared to conventional hydrogen production.
5 million tons, that's roughly the same as taking 1 million cars off the road.
It is significant.
Yeah.
But the real value here, I think, is that it is a proof of concept at scale.
Explain that.
For years, skeptics, and there were many, said this just couldn't be done. They said, green hydrogen is too expensive. You can't run a chemical plant on intermittent wind and solar. The batteries are too heavy. The logistics don't work.
It was a nice idea that just wouldn't work in the real world.
Exactly.
Yeah.
This project is the rebuttal to all of that. It proves that you can integrate solar and wind with industrial processes. It proves you can finance it. It proves you can build it.
It's a blueprint.
It is a blueprint for a global green hydrogen economy. I mean, if this works in NEOM, it de-risks the entire model for projects in Australia, in Chile, in Namibia, North Africa.
It lowers the fear factor for the next bank that has to sign a multi-million-dollar check.
Precisely. It turns green hydrogen from a science project into an asset class.
That is a huge shift. We're moving from the experimental phase to the industrial phase.
And that changes the map. We talked about exporting weather. If this model works, we might be seeing the rise of electrostates.
Electrostates.
Countries that define their geopolitical power, not by their military or their oil reserves, but by their ability to generate and export renewable electrons and molecules.
That is a wild thought. The superpowers of the 21st century might just be the places where the sun shines brightest and the wind blows the hardest.
It's a distinct possibility.
So just to recap the journey we've been on today, we have the world's largest green hydrogen plant sitting in the Saudi desert. It's powered by a sci-fi array of 250 wind turbines and millions of solar panels. It uses that power to split water, turns the hydrogen into ammonia to make it shippable,
and then sends it off to decarbonize the world's heaviest industries.
And it's about 90% built right now in January 2026.
With the tap set to open in 2027. It's an alchemy of finance, physics, and geography.
It really is. You know, we can get cynical about the pace of change. We see the climate reports and it feels like we're moving too slow. But looking at this deep dive, it's a reminder that when the capital and the engineering align, humans can build incredible things very, very quickly.
It gives you a sense of agency. The technology isn't waiting to be invented. It's right here. It's just a matter of deployment.
Before we wrap up, I want to leave you with a final provocation, a thought to chew on. The source material calls this a blueprint. So if this massive experiment works as planned in the next 12 months, if the ships start sailing and the lights stay on, does this signal the end of the experimental era of green energy?
That is the trillion-dollar question, isn't it?
And more importantly, what happens to the global economy when sunshine becomes a tradable commodity, when a barrel of oil is replaced by a tank of ammonia?
The world gets a lot cleaner, and the trade routes get a lot more interesting.
Something to mull over as you go about your day.